Run a thumb down the side of the nearest molded object: a kettle, a keyboard bezel, a door card. To the eye, it reads as flat, but physically, every face running parallel to the direction the mold opens carries a taper. That crisp highlight you see running down the side, that is often the draft angle, not the original styling. This hidden geometry is one of the largest uncredited authors of mass-produced form. Yet the industry habit treats draft as a mere tooling detail, something an engineer bolts on once the design is supposedly finished. This usually happens late in the process, under severe schedule pressure, when making changes costs the most. If you leave a wall perfectly vertical in the concept phase, you are handing the final geometry of your surfaces to someone else at the end of the line. Leaving draft to be added later means you surrender the authorship of your own work. To understand the physics of extraction, look at this cross-section of a steel mold pulling away from a plastic part. Draft is the vertical taper allowing the part to break contact immediately, instead of scraping. The standard rule is 1 degree of draft per inch of depth. Apply that to a 100 millimeter deep wall, and the geometry shifts, finishing almost 2 millimeters thicker at its base than at its lip. A shift of this scale dictates the object's section, clearance, and silhouette, far exceeding any standard manufacturing tolerance. And that standard math breaks down entirely the moment you introduce a surface texture. Surface grain is a microscopic field of undercuts in the steel, physically locking the plastic. To get the part out, the draft angle must increase dramatically, creating enough taper to shrink away and travel upward without colliding. The old industry rules suggested minor adjustments for this. But current tooling data shows that a heavy, leather-like finish requires roughly 6 to 7 degrees of draft. The material itself changes the math again. At the exact same roughness, a rigid polymer like polycarbonate can require twice the draft angle of nylon. Deciding to deepen a texture late in the process is a geometry decision arriving long after the model was supposed to be frozen. Inadequate draft produces immediate physical consequences on the factory floor: severe drag marks, surface scuffing, and damaged molds. Parts stick and fail ejection, which can cause demolding failures resulting in scrap rates as high as 20%. When a vertical draft simply won't work, engineers must build a mechanical workaround. This schematic shows a complex mold utilizing a side action. Instead of pulling straight up, a secondary mechanism physically pulls horizontally to release trapped plastic. These mechanisms are complex to build, require constant maintenance, and can inflate tooling costs by up to 30%. By ignoring demolding physics during the concept phase, a designer can accidentally author an undercut that requires these expensive mechanisms to fix. Treating draft as a foundational tool allows you to take total control over the final form. Active authorship means you choose exactly which face carries the taper. You decide what highlight it throws, and whether that angle seamlessly dies into a shoulder. Toyota proved this approach by patenting it. Look at this cross-section of a car bumper. They moved the mold's parting seam off a flat, highly visible surface, snapping it perfectly onto an intentional styling crease. They took the tool's absolute mechanical requirement and turned it into a deliberate visual feature. Take the surface model you are proudest of. Without opening the file, can you answer this? Which way does the tool open, and where exactly did you put the degree of draft? If you cannot say, someone else in the supply chain will answer it for you, and you will read their answer in the highlight. Design iterations cost almost nothing at the sketch phase. They become brutally expensive and rigid once they are cut into steel. Seeing these angles before the mold is cut ensures that the final product remains exactly as you intended.